Hello, our names are
Laura
and Sebastian, and today we're going to explain the power method for X-ray diffraction for the unit cell of potassium.
Game start!
So X-ray diffraction involves many variables that we need to consider to get the analysis of whether it has a BCC or FCC structure. So first of all, we learned in class that the squared sine of theta of A, which is like on one point or one peak of the X-ray diffraction graph that Vesta showed, which will appear somewhere around the screen, divided by another squared sine of theta in another peak. And if it's 0.5, it will be a BCC unit cell structure. But if it's 0.75 or approximate, it will be an FCC base cube structure. So we have that the formula of the distance between HKL, which are the coordinates in y, x, z of the different crystallographic planes that are crossing through the unit cells, is the lattice constant A divided by the divided by the magnitude of the three coordinates. So if we solve for A, we get that A is equal to the distance between the coordinates and the magnitude. So we also have Bragg's law, which tells us that lambda, which is a constant. Let me explain lambda a little bit further. It's the distance times sine of theta. So lambda is a constant that is used to, it's like a ray. When you're doing X-ray diffraction, it tells you, and while it's okay, so we have the pulverized potassium that is the one that we are now analyzing right now. So it's twisting, and the light, it's mixed with, I think, copper, and that's why it's mostly always copper, the element that we use for X-ray diffraction. That's why lambda stays constant. So now we have that lambda is also equal to 2 times the lattice constant, multiplying the sine of theta divided by the magnitude of the coordinates, and when we solve for the sine of theta, we get this formula. But what we're actually going to use, since Vesta gives us the number of peaks, it gives us 2 times theta, and it also gives us the coordinates of the crystallographic planes that are passing through each and one of the peaks. Since we only have that information, we will be using this and this formula, which is the distance of the coordinates of the crystallographic planes being equal to lambda divided by 2 times the sine of theta, and the solved for the lattice constant in terms of the coordinates of the crystallographic planes. So now my classmate Laura is going to explain how we know that potassium has a unit cell with a structure of body-centered cube.
In the chart, there are 7 columns. Peak, the order number of the peaks in the diffraction pattern. 2 theta, the total of the angle diffraction. Theta, since we need theta alone to then square the sin to apply the Bragg's law and convert the answer into radians, because this is how the sheet works. And it's where we're building the chart. Sin squared, to follow the formula mentioned before to determine the structure. To then, with the help of the Miller index that generates each peak. Finally, the lattice constant, so to solve the parameter using the rearranged Bragg's formula to find the size of each cell. Following the graph provided by Vesta, we just get theta and the Miller indices. And now with the 17 values, we will get an average that you can see now. And with the 2 first values, in this case these 2, like you can see, you will get, by applying the formula, a 3.499, and this will let us know that it is a BCC structure. So now we're going to build a chart. We will first put in the first value for the first peak, in this case 25.5. This will solve the rows automatically. And the next one being theta alone divided by 2 to get the value, and then multiply it by since in this case it's always by radian, since this is how the sheets work, to then square it to have a better view of the values. And now this value will be multiplied by lambda like shown below, and we will get the value to follow along with the formula and get the lattice constant applying the rearranged Bragg's law. We will do this with all the peaks, in this case 17, since this is what the graph shows. Now the second one is going to be 36.3733. Now we get all the values we need. So now finally we have calculated the parameters for the potassium lattice constant, a BBC crystallographic plane.
Game start! 아파트